Hello everyone, and welcome back to another GIS statistics lecture video. And in this video, I want to wrap up our discussion on second order analysis. In the previous video, we walked through this equation for Ripley's K, and I sort of went with a generic interpretation that, assuming that the area and the number of points don't change, higher means potential clustering, lower means potential dispersion. But just like with the first order, right, it's more useful to have something to compare that to. And the way that we're going to approach that comparison is, again, with an expected value. And from this expected value, we're going to sort of alter this k function to make it a little bit easier to interpret. So what we're going to do is we're going to scroll down, and I want to just lay out what the equation is for the expected value. Right, and just like last time, this is coming from a Poisson distribution. Now, I'm not going to go through all of the algebra involved to get to this point, but if you go through everything, what you end up getting, and this is really nice, is that, right, the expected KD, right, the expected KD, or KR in our case, because we're using R, right, the expected value given a radius is pi r squared. Right, again, I'm not going to go through the entire process of how we managed to go from the Poisson distribution to the area of a circle, but the fact that we did means a lot. And I'm going to show you why. And this I am going to walk through because I want to sort of explain why we do this. Right? In a perfect world, right, our K, I'm going to put a hat over this. Right? This is our observed. Right? Our observed K sub r in a perfect world is going to be equal to our expected K sub r, right? So in a perfect world, this is what we would hope to have. So this is literally an equation, right? Some function equal to another function. Now, in math, right, we can do a lot of things as long as we do them to both sides of an equation. And so what we can do here is we can say that k, our observed value, right, we can replace this with what we've already declared it as, which is pi r squared. Okay. So now what we can do is we can divide both sides by pi. So if we take our observed k and divide by pi, this is going to be equal to r squared. Now we can take the square root of both sides. Okay, so if you don't understand what this means that our graph, actually let's keep that because that's actually going to be useful. Let's keep that. Right, this means that our graph of our distance, right, if we plot this thing, you're going to end up with a straight line. If that doesn't make immediate sense, I'm going to repeat that. If we graph this thing right here as a function of distance, we would hope to get a straight line. And what you'll often see is you'll see this thing here denoted as its own parameter called L sub r. And you'll see that as usually equal to the square root of k sub r over pi. Right? But if you take that step to divide by pi and take the square root, right? So this would be L sub r. Right, the expected value of L sub r is just the distance. Right, so this becomes our expected. If I'm rushing through this, I encourage you to pause the video, go back and rewatch the parts that I'm going quickly through, and just sort of keep in mind that this is very similar to what we did with the first order analysis. So maybe go back and watch that video as well to sort of understand where I'm coming from and hopefully where I'm going to with this. Okay. So basically what we've done now is by calculating the L sub r, right, by taking this process of dividing by pi and taking the square root, right, we've made our expected value a straight line. And so what that means then is that means if, I'm going to just use L here, right, if L is now greater than R, this indicates clustering. Right, now if L is less than R, this indicates dispersion. So for a given radius, if you do this process to go from K to L, right, you're basically just comparing your L value to your R value. And if it's greater than it, it means you likely have clustering. If it's less than it, that indicates dispersion. And we can do the same thing again, right? We can do that same process again here with the graph, where we graph the L value as a function of distance. And again, our expected now is just this straight line. And so what you'll see with L is that L will hopefully be a perfectly straight line, but you might see something that looks like this. And so what this would mean, right, just like before, right, where your L is greater than your distance, right here, right, this indicates clustering. Right, and by the same token, right, areas where your L is under the line, right, it's where it's under the expected, right, this indicates dispersion. Okay, so hopefully that makes sense. Hopefully you followed along. Again, getting the expected to be pi r squared. I wouldn't expect you to understand how we got to this point, but just accepting that this is true, being able to understand how that gets us to this L function and how that makes this a line really helps make interpreting the graph and interpreting the results a lot easier. So hopefully this made sense, and if you have any questions, please reach out. Thank you.